are investigating how the surrounding temperature affects the rate at which the water cools. They are using the apparatus as shown in figure 1.1. So you can see the apparatus that there is a hot water in a test tube and a cold water is there in a beaker, and there is a hot water in a test tube and warm water there in the beaker. Using figure 1.1 and state the temperature theta A. Theta A means the temperature of the water in beaker A, and theta B means the temperature of the water in beaker B. What is the temperature theta A? Theta A is 18. Always write the unit. And what about theta B? The temperature of the water in the beaker B. That's 37 degrees, so we will write 37 degrees. The next part, the test tube of a hot water are placed in a beaker A and B. The student record the temperature theta of a water in a test tube every 30 seconds. And their readings are shown. Complete the table, complete the units and the time column in the table 1.1. So complete the units. First one, the time is there, so unit will be second. Theta is the temperature, that's degree centigrade, and theta, that is also degree centigrade, the temperature. Then student record for every 30-second interval. So 0 is there, 30 is there, 60, 90, 120, 150, and then 180. Because these are the temperature, these are the time interval, because student record for every 30-second interval the temperature. So basically what student did, he just placed this test tube of inside the cold water, and then he placed the test tube inside the warm water, and he recorded the temperature of the test tube, the water in the tube in beaker A and beaker B. The next part, describe 2 precautions that you would take before reading the thermometer to ensure that the temperature readings are accurate as possible. Like what student is doing, student is placing this test tube in a cold water and then in a hot water, and he's recording the temperature. So what precautions we should take to ensure that our results are reliable, our results are accurate? We should look perpendicular to avoid a parallax error. That is one thing. So we should look perpendicular. To avoid a parallax error. What else we can do, because we are measuring, or we want to measure the temperature accurately as possible. So we should wait for the temperature to rise or temperature to be constant and then record the temperature. So look perpendicular, that is one thing. And when you're recording a temperature of a liquid, the liquid might not have a uniform temperature throughout. So to have a uniform temperature or same temperature, you can stir before recording a temperature. You should keep the thermometer at the same level, that's right. Or you can wait until the reading or the temperature stop rising. Once it stop rising, that temperature you will read. And if you are measuring the temperature and the time together here, as we had seen in the table, we are measuring a time first and then we are measuring a temperature. So the two apparatus, the two instruments should be placed next to each other. So what precaution we should take? We should look perpendicular to avoid a parallax error. We should wait for temperature to constant, and then what we should do, we should use the same level, like the thermometer, keep the thermometer at the same level every time we are doing. And because when you are measuring a temperature of a liquid might not have a uniform temperature throughout, so you can stir so that throughout the liquid it will have a uniform transfer of heat energy and at having a constant temperature. So stir before taking the reading. So these are some regarding insulation, because what happened, you are finding the effect of surrounding temperature on rate of cooling. So if you use the insulation, so you are cutting off this apparatus from the surrounding. That's why using insulation will not award a mark here. As you can see, the objective of this experiment is to investigating how the surrounding temperature affects the rate of cooling. So if you insulate, it will not have any effect of the surrounding. That's why the term insulation or insulate is not awarding any mark. Write a conclusion stating how increasing the temperature of a surrounding affects the rate of cooling of a water in a test tube, and justify your answer with reference to the table. So how the rate of cooling is affected, as you can see, a test tube A is there, a test tube in beaker A which is in a cold water. So after 180 seconds, what is the temperature change after 180 seconds for beaker A, for the tube in beaker A? That is 51.5. And what is the temperature change for a tube in beaker B which is in a warm water? The temperature difference from the beginning till the end, that is 35.5. So which tube the water cooled down quickly? A tube in beaker A with cold water and tube in beaker B with warm water. So which one will cool down? So tube A will cool down faster, because you can see it's having a low in a tube in a beaker A with a cold water cool down faster. And you can clearly see, because a cold water, when you have a container which is filled with the cold water, so a container filled with the cold water may be example. And what was the temperature of the cold water? As you can see in the beginning, you mentioned it was 18. And we place a tube inside which is having a water at 80.5, and we repeat this procedure with a hot water That initial temperature of the hot water was 37, and the tube inside this hot water at a temperature of 81. The water is there inside the tube, which is having a temperature of 81. But after 180 seconds, after 3 minutes, you will find that in beaker A, the water cooled down quickly as compared to that in beaker B. So what it shows when we have a greater difference between the initial temperature, because this is the initial temperature and this is the surrounding temperature. Surrounding is the water. And this one is the initial temperature and this is the surrounding. So when we have a greater difference in the initial temperature and the surrounding temperature, the water will cool down faster as there is a lower temperature as compared to that of when it is in a warm water. So what we have to do using a reading, we have to write a conclusion with reference to the table, readings in table 1.1. So what we can say the rate of cooling increase or proportional to as the temperature difference between the temperature difference between the water in a tube or the water in the beaker increase, or the temperature difference increase. And with reference to reading, how you can work out with reference to reading? So in beaker A shows a temperature change of 51.5 compared to beaker B, which shows temperature change of 35.5 in 180 seconds. Is it clear to everyone? So with reference to the reading, you have to write the conclusion. Then suggest one change to the experiment shown in figure 1.1 to ensure that the comparison of effect of surrounding temperature on cooling is a fair test. So basically, what parameter can be kept constant for a fair comparison?
Surrounding temperature.
No, we are finding the effect of surrounding temperature on the temperature of the water to cool down. So surrounding temperature should be different. It should not be same than same initial temperature of the water. The hot water in a test tube should be in same initial temperature. Then same amount of water, as you, even if you check this, they give you the answer in the question. As you can see here, we have a greater amount of hot water in the first experiment as compared to second experiment, and the amount of cold water which we are using in beaker A is less as compared to a warm water in beaker B. So for a fair comparison, we should take an equal volume of the hot water in a tube. So what we can do for a fair comparison, we should take a same volume of water in the tube, and how it will affect, because different volumes have different rate of cooling. Like if you have greater amount of water, or it will take longer time to cool down as compared to small amount of water. So the things, it's many possible answers for this. You can mention the volume of the water in the test tube should be same. An explanation, the rate of cooling is affected by volume of the liquid. So you can mention these things, and same starting temperature as well. You can mention, because the water, the tube in the first experiment, the tube was at 80.5, but in the second experiment it is 81. So different initial temperature. So for a fair comparison, we should have a same initial temperature of water in a tube for beaker A and B, because the initial temperature, the starting temperature or higher initial temperature will have a greater rate of cooling, because we are only finding the effect of surrounding temperature on the rate of the cooling. The student, using a measuring cylinder to measure 200 cm cube of cold water, describe how to read the measuring cylinder to obtain an accurate value of the volume. You may draw a diagram. So what we should do, it's of 2 marks. So if we have a measuring cylinder which is filled with 200 cm cube of water, we always read the lower meniscus and for measuring cylinder, one side we have a scale or the marking, so we should look perpendicular from the side of the marking to avoid a parallax error. So if in the question they say you may, then you should draw a diagram, because maybe your explanation is not complete. So look perpendicular at a lower meniscus to avoid a parallax error. So when you draw the diagram, it will complete your answer. The next part, a student is investigating the resistance of 3 wires A, B, and C. He is using a circuit shown in figure 2.1. The circuit is set up to test wire A of length L. The length L of each wire is measured and recorded. So this is wire A, B, and C. On the figure 2.1, draw a voltmeter connected so that it can measure the potential across wire A. So that we can measure the voltage across wire A. You can use a screen annotation to show the position of the voltmeter, where we should connect a voltmeter to measure voltage of wire A. Voltmeter is in parallel, that's true, but look, if you connect a voltmeter on these ends, so this will not give us the total voltage, it will only give the voltage drop in this part. So we want the total voltage across. So if you want the total voltage, what we will do, you can connect parallel to this whole wire. Even you can connect here, that's same, but if you connect only for this part, then what you will get, you will not get the total voltage, you will get the potential only, the voltage drop within this part.
So sir, can we draw here, like here?
If you draw at this part, so you are getting a voltage in this part only. But in the question they are asking to measure the potential across wire A. So it must be parallel to wire A.
Okay.
Okay. So as it must be parallel to wire A, so I can just make a voltmeter. These connections are already there, so I'll get a voltage what is dropped across wire A. And voltmeters are always connected in parallel. in the figure, in the first line of a table, 2.1, record the potential and a current as shown. So what is the voltage reading and what is the current reading? The voltage reading, 2.7, that's right. And what about the current reading? What is the current reading for an ammeter? Each value is 0.02. Each line is, so it will be 0.48. Now to get the resistance dimension, so in this part dimension that we have to complete the last column. This is 2.7 and this was 0.48. You don't have to learn a formula here, just use the formula given in the question. Resistance is voltage divided by current and write the values. So complete this column using a screen annotation. Voltage divided by current, 2.7 divided by 0.48. When you write your answer, the number of the significant figures are important. So when you complete it, like the first one is 5.625. So if it is 5.625, so you can round it off this to 5.63 or 5.62 you can write. So 5.63. And the second one is when you divide 2.4 with 0.75, what is the answer for this? 3.2. But because you are using a 2 decimal places or 3 significant figure, so you should write 3.20. And the last one, which is 2.59, so you will write 2.588, so you will get 2.59. So these are the values for 5.63, 3.20 and 2.59. Number of significant figures are important, so you should use same number of significant figure when you are completing a column. Calculate the resistance per unit length for each wire using an equation. R is equals to resistance per unit and include a unit. So how to get a resistance per unit length means you have the resistance here. The first value, this was 5.62. This was 2.59 and this was 3.20. Next part, you have to calculate resistance per unit length. What is resistance per unit length? Resistance divided by length. So what is the resistance per unit length for wire A? Means 5.62 divided by 0.9. What is the answer for this? So the first value, when you divide them, it is 6.24. Not in this column, we don't have to complete here. This is a voltage value, that is 2.7 and the current was 4.8. We have to complete in this part the resistance of A, that is equals to 6.24. With a suitable unit, The unit for resistance is ohm and unit of length is, because that was given in meter, so it will be ohm per meter. What about the resistance per unit length for wire B? The resistance is 3.2 and the length is 0.5. So 6.40 ohm per meter. And what about the third one? 2.59 divided by 0.4. 2.59 divided by 0.4. You're using the same number of significant figures, so 6.48. Because 3 significant figure first answer, so all the answers should be in same number of significant figure. That's why. Now in the next part, they're asking, another student suggested that R should be same for each wire. Like the first value of the R was 6.24. The second value of the R was 6.4. And the third value of the R is 6.48. So another student, what he suggested? He suggested that all the values like the R should be same for the wire. Another student suggested that R should be same for each wire. State whether your result supports this suggestion and justify with reference to your result. So basically we want to show that these all values are same. So if you want to show that these values are same, what we can work out, or how we can work out, we can use a percentage difference. What is the formula for percentage difference? The percentage difference is the maximum value divided by the minimum value, maximum value minus minimum value divided by the mean or the average into 100. So the maximum value in the combination is 6.48. The minimum value is 6.24. Divided by average, what is the mean of 6.48 and 6.24? The average, add them and divide by 2.
Sir, it's maximum minus minimum over what?
Divided by mean, average, MEAN. So 6.36 into 100. So what is the answer for percentage difference? 6.48 minus 6.24, that will be equal to 0.24 divided by 6.36 into 100. The percentage difference is how much? 3.77 or 3.78. So our statement should be yes, and the reason the percentage difference is less than 10%. So within limit of experimental accuracy, the values are same. So comparison of the value is always done with percentage difference. The student measured the length of each wire to be tested. On a figure 2.4, draw an arrow to indicate precisely between which 2 points should we measure the length. So which 2 points we should measure the length? You can use a screen annotation for this. Normally when we use a crocodile clip, so yeah, that's right. Hashim, inside, not till the far inside edges of a crocodile clip, we should measure this length. The next part, when you draw, because we want to measure the length of the wire, so it should be closer to the wire and next to the inside part of a crocodile clip, which we can measure as the length of a wire used for the experiment. One possible problem with this type of experiment is heating of a resistance wire. Suggest a precaution that could be taken to reduce this. Because in electricity experiment, the one problem is it produces heat. How we can minimize the heating effect? What we can do? Heating effect. It's not like heating effect. We want to reduce the heating effect. It's not like we are catching the wire or holding the wire. Plastic coating is normally for. So basically heating effect is based on the current. So what we should do, we should increase the resistance. How we can increase the resistance? By using a thinner wire. So what we can use a thinner wire, or we can use a longer wire, or we can use a low voltage or current supply. And there's also a one way that switch off between the readings, because if your circuit remain on for a longer period of a time, so it produce a greater heating effect. So you can switch off between the readings, like once you use your apparatus, you recorded the voltage and current, you can switch off the circuit and switch on again to measure the voltage and current for the second set. Question 3. Some students are investigating the magnification produced by a converging lens or a convex lens. They are using this apparatus. The apparatus is there, illuminated source, a lens is there, and the screen. A student set the distance u. Paper 6, you will find many repetition or questions repeated many times. So if you practice like sessions, like 7 to 8 sessions, that is sufficient. So some students are investigating the magnification produced by a converging lens. They are using the apparatus shown in figure 3.1. Illuminated triangle is there. So basically it's an illuminated triangle, but when the light passes through a convex lens, on the screen we'll see an inverted triangle, because image formed by a convex lens or real images formed by the convex lens are always inverted. The student set the distance u between the illuminated triangle and the lens, that is 20 centimeter. She moves the screen until a sharp image of a triangle is seen on the screen. The height of the object of this triangle was 1.5. Measure and record the height of the image. This is actually an image, and it is true that it should be an inverted image because it's a real image. Real images which are formed by a convex lens are always inverted. So you will use a ruler scale, just measure this height. So right now, because we are not doing this using a hard copy, so I'm taking the value which is given, example 4.5 centimeter. But you will use.
Sir,
Yes?
I have a question. Sir, how will the light travel straight?
How?
How will the light travel straight? I mean, it will bend. It will refract.
Diffraction can occur, but diffraction only happens if the wavelength matches with a gap. Yeah, I got your point. What you're saying, the light should. No, this is a converging lens. So converging lens converge the light rays. Basically what happened, the light which is traveling from top part will pass through the focus, and one through the optical center will pass straight. The point where these two light rays will intersect, that is the position we'll see a tip of the image. So if
Okay.
object is like this, the image will be inverted. But
Okay.
as the screen distance and the lens distance is more, so it is obvious that the size of the image will be larger than the object. So the height of image, example 4.50. Then we have to calculate m. How to calculate m? They give you the formula. Then m is hi over ho. What is hi? Hi is given. And what about ho? Ho is 1.5. So to get magnification, it is hi divided by ho. Hi is changing, but ho is 1.5. So each value is divided 1.5. So 4.5 divided by 1.5. That's 3. The second value, 2.25 divided by 1.5. That's 1.5. 1.1 divided by 1.5. So I'm taking one decimal, so 0.7. 0.75 divided by 1.5, so 0.5 will be there. And the last one is 0.55 divided by 1.5. That's equal to 0.36. This value was how much? 1.1 divided by, so 0.73. Okay.